Alright, I want to welcome everybody to today's webinar. This is Colored Glass Solutions for Engineering Brief 67D. My name is Rick Miner. I will be your host today. Our presenter will be Adam Tomeno. He is COPS production engineer. He's been here approximately 4 years. So with that said, I will leave it to Adam.
Thank you very much, Rick. I'd also like to welcome everybody to today's presentation on Colored Glass Solutions to Engineering Brief 67D. The purpose of today's presentation is to educate everyone in this webinar on some of the color implications associated with Engineering Brief 67D and how LED lighting is going to have an impact on taxiway edge lighting and obstruction lighting. We'll start things off by having a brief overview of Engineering Brief 67D and some of the key aspects out of Engineering Brief 67D. We're going to then discuss the color requirements associated with Engineering Brief 67D. We'll talk about the individual parts that are affected by Engineering Brief 67D in both the aerospace and the obstruction lighting field. We're then going to talk about different avenues for achieving the chromaticity that you desire in conjunction with Engineering Brief 67D. Light source binning, a very important topic in the LED arena, and then we're going to talk about COPS solutions and testing capabilities. Okay, so why was Engineering Brief 67D drafted? Engineering Brief 67D was drafted to provide additional requirements for light sources other than incandescent xenon lighting fixtures used in the aerospace and obstruction lighting industry. There's several documents you need to be familiar with before you can really dive too deeply into Engineering Brief 67D. Some applicable documents are Aviation Circular 150 5340-26 30, as well as Aviation Circular 150 5345 43 46 and 53. I'm not going to go through each of these documents during this presentation, but I just want to leave this slide up here for you to use as a reference for your own purposes. One of the key factors to pull out of Engineering Brief 67D per a memorandum issued in March of 2012 is the effective date for Engineering Brief 67D. And the effective date for Engineering Brief 67D is December 15th of 2012. Lighting qualified under Engineering Brief 67A, B, C, or SAE 25050A must requalify if it does use a light source other than incandescent or xenon lighting. The FAA recommends Engineering Brief 67D as a guideline for the standards for sources other than incandescent and xenon fixtures used in aerospace and obstruction lighting. And in general, Engineering Brief 67D is not mandatory. However, Engineering Brief 67D is mandatory for all projects funded by federal monies through the Airport Improvement Program and with revenues from the Passengers Facilities Charges Program. For more information, see the reference documents at the end of this page. Fixtures must be tested for conformance to Engineering Brief 67D using a spectroradiometer at increments of 2 nanometers or less. Testing must be conducted after an applicable warm-up period per the Aviation Circular. The typical warm-up period for most fixturing is 15 minutes or greater. While Engineering Brief 67D isn't LED specific, the chromaticity requirements and addition of LED binning nomenclature suggests that Engineering Brief's color requirements were defined with LEDs as its primary focus. The chromaticity requirements for Engineering Brief 67D may look familiar, and that's because they're really a collection of chromaticity requirements from various specifications, both domestic and international. So, what exactly is affected by Engineering Brief 67D? The chromaticity requirements for all the following fixtures when using a non-incandescent or xenon light source, an LED light source, in the runway and taxiway industry per previously AC 150 5345-46D are now subject to Engineering Brief 67D. And if you'll notice, the FAA designation now features a bracketed L next to the FAA designation name for the fixture. This denotes that it's now using an LED light source. And so, like I said previously in the presentation, sort of gives you the impression that Engineering Brief 67D was written with LED lighting as its primary focus. Additionally, taxiway and pavement lighting is subjected to Engineering Brief 67D. Again, this is previously from the Aviation Circular 46D specification. And elevated lighting, previously from the 46D specification, is also subjected to Engineering Brief 67D when it uses an LED or non-incandescent xenon light source. In addition to runway and taxiway edge lighting, some obstruction lights are also subject to the chromaticity requirements defined in Engineering Brief 67D. You'll notice next to the FAA designation for these parts, there's also an L in parentheses, designating that a non-incandescent or xenon light source was used. These parts are called out in Aviation Circular 150/5345-46 for obstruction lighting. So, what is not affected by Engineering Brief 67D? There are some obstruction lights called out in Aviation Circular 150/5345-43 that are not affected by the new chromaticity regions defined within the Engineering Brief. All of those obstruction lights are red obstruction lights, either solid state or flashing lights, and they're subjected to the chromaticity requirements, the red chromaticity requirements for ICAO Annex 14, Volume 1. There are several parameters to consider when selecting lensing for a non-incandescent fixture. These parameters include selection of the appropriate light source and filter, because the filter and the light source are your major drivers for your final chromaticity. The photometric requirements as defined by AC 150/5345-43 for obstruction lights and 150/5345-46 for runway and taxiway light fixtures. Engineering Brief 67D also has a daylight viewing requirement for all fixtures that are elevated airport fixtures. This includes L860E, L861T, L861E, L861SE, and L862E. All these fixtures must have a minimum daytime visibility of 2.5 square inches when viewed from any direction using a horizontal viewing angle of 0 to 45 degrees. Another important aspect to consider is the chemical and physical durability requirements of the Aviation Circular 46D, including the abrasion requirements, thermal requirements, and corrosion requirements that the fixture can be subjected to. The fixture does include the lensing. There's a number of ways to go about achieving your desired chromaticity when using an LED light source and a filtered piece of cover glass. But the important aspect to remember is that both your LED and your filter dictate your final color. Options include using a white LED with colored cover glass, using a colored LED with clear cover glass, and using a colored LED with a colored piece of cover glass. Each of these options has its advantages and its disadvantages. For instance, a white LED with a colored piece of cover glass. One advantage is a reduction in electrical component inventory, since a single LED source and driver combination is used across all fixtures. Another advantage is the daytime visibility of the fixture. Using a single source also simplifies the binning and heat sinking requirements, since all fixtures will have the same thermal binning binning limitations. Some of the disadvantages to using a white LED in a colored piece of cover glass include a low light output to energy efficiency ratio. It's also difficult to achieve a very deep green color saturation level due to the low green output of most phosphor-covered white LEDs. And it also increases the fixture design requirements for your fixture. The next option for achieving chromaticity compliance with Engineering Brief 67D is to choose a colored LED within your fixture and a clear piece of cover glass. One advantage is a very high transmission and subsequent high photometric efficiency. This also translates to a very high light output to energy consumption ratio. Another advantage is a very high level of color saturation, since your LED's dominant wavelength is really the only driver for color in this system. One of the major disadvantages to using a colored LED with a clear piece of filter glass is no daytime visibility on the lens itself. Another disadvantage to using a colored LED source and a clear piece of cover glass is the increased LED binning inventory for fixture manufacturers. It's difficult enough to select one LED with the appropriate binning, so having multiple LEDs for multiple fixtures increases that difficulty. Driver variability is also another disadvantage, selecting the appropriate driver configuration for each LED. The major disadvantage to selecting a colored LED with a clear piece of cover glass is the high level of variation within LED dominant wavelengths, even within the same bin. Some of the advantages of using a colored LED with a colored cover glass include higher overall transmission and corresponding photometric efficiency. Your colored filter acts as almost a safeguard against falling out of specification, and you achieve an even higher level of color saturation than you would with just a colored LED alone. Some of the disadvantages to using a colored LED with a colored cover glass include increased inventory for manufacturers, having both extra lenses and light sources on stock. Driver variability is still a problem since each LED has to be driven a little bit differently, and very high level variation within LED binning. As I mentioned earlier in the presentation, one of the major obstacles associated with using an LED light source is complications associated with LED binning. LED binning refers to manufacturing practices in which LED manufacturers separate LEDs into various sub-classifications based on their spectral distributions and photometric output. There currently isn't an industry-wide LED binning criteria, and so each manufacturer has the ability to choose their own criteria for separating their LEDs into sub-bins. The tolerances that manufacturers choose for binning their LEDs vary drastically from manufacturer to manufacturer. This can be problematic for both white and monochromatic LED sources, and it's a factor that should be taken into consideration when selecting where you're sourcing your LEDs from. Due to the absence of an industry-wide LED binning criteria, many white LED manufacturers have adopted criteria used in fluorescent lighting to classify their LEDs. One such adopted criteria for LED binning is in the ANSI C78377-2008 specification, which defines various chromaticity regions for fluorescent lighting based on visible color temperature. Direct adoption of this fluorescent lighting binning specification into the LED market have proven problematic. This is because of the significantly higher color temperature associated with white LEDs, thus their more blue appearance. To compensate for some of the shortcomings associated with the ANSI specification, NEMA has recently released a series of guidelines intended to address LED binning specifically. As you can see by the graphical depiction below, there's significantly more sub-binning going on within the NEMA specification than the previously shown ANSI specification. At this point in the presentation, I'd like to go over several examples of how we can comply with Engineering Brief 67D while using an LED light source. As we mentioned earlier in the presentation, you have several options when trying to achieve an end chromaticity and using an LED source, white or colored, and a piece of cover glass, colored or clear. All of the examples that we'll work through today are specific to the Engineering Brief 67D green specification. However, the same principles would apply to other color chromaticity requirements. The first example that we're going to work through is a generic white LED with a green cover glass. In this example, a very color-saturated green piece of filter glass is necessary to achieve the desired chromaticity. The result of using such a color-saturated piece of filter glass is a very low relative transmission and corresponding overall photometric output. The 4 dots on the CIE 1931 chart correspond to the spectral distribution shown above. Note that all 4 spectral distributions are relatively similar, however their location on the CIE chart varies slightly. To illustrate why it was necessary to use such a color-saturated piece of filter glass, we'll move to our next example on the right. In this example, the same 4 generic LEDs from various bins are used in conjunction with a much higher transmission piece of filter glass. Notice that while there's a threefold gain in overall transmission, the corresponding CIE coordinate position for all 4 light sources is well outside the Engineering Brief 67D green specification. The takeaway from comparing these 2 examples should be that in order to achieve a deep green level of saturation when using a white LED source, a very green filter is necessary. In our next few examples, we'll look at using a green LED to drive your fixture system. Again, the spectral distributions for the LEDs of various bins are shown above. Notice the high degree of variation within dominant wavelength position from one LED to the next. This should stress the importance of binning when selecting your LED. In the example on the left, a high transmission piece of green filter glass is used in conjunction with the green LEDs. Note the increase in transmission using a green LED in conjunction with a green piece of filter glass versus the previous 2 examples. In our next example, we'll examine using a generic green LED with a white piece of filter glass. Again, the variation in LED dominant wavelength from bin to bin should be noted. The corresponding CIE diagram on the lower right-hand side of the slide shows the position of each LED when used in conjunction with a white piece of filter glass. Just like in the previous example, LED bin 6 with dominant wavelength of 545 falls outside of the Engineering Brief 67D specification. Note that this example has the highest transmission of all 4 examples worked through today. This higher transmission also corresponds to higher photometric output and thus overall energy efficiency. A comparison of the CIE charts in both of these examples shows that a much higher degree of color saturation is achieved when using a green LED in conjunction with a green filter than using a green LED with a white filter. However, the trade-off is a reduced overall photopic transmission. Several additional factors to consider when complying with Engineering Brief 67D are that the LED industry is rapidly evolving. A general rule of thumb when designing a new fixture around an LED source is to use the brightest LED technology that's currently available. This will put you in the best position for future LED technologies coming down the pipeline. Unlike traditional incandescent and xenon light sources, LEDs last forever, depending on what your definition forever is. It's important to define end of life for an LED when designing a fixture. The burn-in period for an LED is not a linear function. In fact, most LEDs experience a 5 to 10% increase in photometric output during the first 1,000 hours of life, at which time they decrease back to nominal. The LED's intensity then decreases slowly over time. One of the most important factors to consider when selecting an LED for a fixture is the reputation of the LED's manufacturer, their binning practices, and the quality of their product. So, why use glass lensing in your Engineering Brief 67D compatible fixture? For one thing, the physical and chemical durability requirements defined by Aviation Circular 150-53-45-46D still apply to Engineering Brief 67D compatible fixtures. This includes the abrasion, thermal, and corrosion requirements. Colored glass lensing is an easy way to achieve the daytime recognition requirements defined by Engineering Brief 67D, Section 2.8. The color of glass lensing will not change or degrade over time. The strength of glass lensing, particularly borosilicate glass lensing, provides protection for your light source and all critical electronics within your fixture. Glass also provides UV protection for your light source and all electronic components. In harsher environments, thermal toughening is also an option for glass lensing. Cop Glass has developed some LED-specific glass compositions intended for meeting the challenges of Engineering Brief 67D, as well as other LED-specific lighting requirements. Our LED-specific glass formulations include Aviation Blue 2004 and our 3120 Series Blue, Aviation Green 4786 and our 4650 Series Green, Aviation Yellow 5600 and 5701, and our Aviation Red 6150, 6250, and 6350 glass formulations. In the past year, COP announced the installation of our Sapphire Technical Systems AP48SD goniophotometer. This instrument allows COP the ability to take photometric measurements from any angle, from intensities ranging from 1 millicandela up to 2 million candela. And that concludes our presentation for today. I want to thank everyone for spending the last 20 minutes or so with Rick and I to look at some of the different complications that are associated with Engineering Brief 67D. Thank you all very much for attending.
Okay, thank you, Adam. For those of you who have submitted questions during the webinar, we will answer those questions via a follow-up email, so keep an eye out for that. Also, if you are attending IES ALC 2012, our Manager of Process Engineering, Matthew Bogart, will be giving a presentation on LED-compatible colored filter glass solutions for infrared aerospace applications. If you cannot make it to IES 2012, we will also be giving this presentation in a webinar format, so keep an eye out for the announcement in November. Thank you for attending. If you have any other questions concerning Engineering Brief 67D, please feel free to contact one of our solutions consultants. I hope you have enjoyed this presentation. We look forward to giving future presentations as well. I hope you all have a wonderful afternoon, and thank you again for attending.